Hi, my name is Caleb Ham, and today I will be teaching you how to take the internal forces of a member and display it as a shear force or moment diagram. I'm currently enrolled in Engineering Science 213 Statics here at Trine, and I have a test coming up this week, so I figured this was a good way to knock two things out at once, and maybe even it might help somebody watching the video. All right, so behind me we have this question from my homework. As we can see, it's a member with a pin supporting it at A and a roller supporting it at C with a distributed load that spans 2 meters. This question asks us to find the support reactions at pin A and the support reactions at pin C, and then to diagram our shear and moment forces along the beam. I'm going to turn off the projector because the lighting's a little weird here, and then we'll get started with the problem. All right, so the first thing we're going to want to do is use our given image and convert it into a single free body diagram that we can use to solve for the support reactions at point A and point C. So first we're going to draw the beam, and then we can represent point A, since we know it's a pin, as a singular X force and a singular Y force. We're going to call these AY and AX. Next, we can represent point C, which is our pin, as a singular Y force. Lastly, we're going to want to represent our distributed load as a single force along our beam to make it easier to solve for our support reactions. To do this, it's pretty simple. We're just going to multiply by our force over the distance it's across. So 1.5 kilonewtons times the 2 meters we get from subtracting 2 meters and 4 meters. And we can see that this singular force of 3 kilonewtons can be used to represent our entire distributed load. And then we know that our distributed load acts in the middle of our distributed area, which will be 3 meters from point AC. Next, we can isolate point CY by taking the sum of our moments around point A and setting that equal to 0. Since we know that our force and our CY are going to be opposite directions, we can express our force times the distances across minus the distance from AY to CY, which we know is 4, and set that equal to 0. From doing this, we can solve for CY equaling 2.25 kilonewtons up. Next, to determine the support reactions in AX and AY, we can do the sum of forces in the X equal to 0 to isolate our AX variable. Since AX is our only force acting in the X direction, we know that AX equals 0. Lastly, by doing the sum of forces in the Y and setting that equal to 0, we can solve for our AY. We know AY is going to be acting in the positive direction because our force is larger than our CY. And setting that equal to 0. Now we can solve for our AY, which is 0.75 kilonewtons. All right, so unfortunately my audio did corrupt, but here I am the next day ready to pick up where we left off. Last thing we did was express our support reactions and make our new free body diagram. Now we're ready to express our forces on our shear plot. It's important to reference our new order of lines chart we have here, which helps us draw our diagram. Basically, it says that any force we can express as a constant, any constant we can express as linear, and any linear we can express as a quadratic. Using this rule, we can start with our force at AY of 0.75 kilonewtons. Since it's a single force, we can represent it as a constant. We know it's going to be at 0.75 because that would be the area expressed by the constant. Now that we've expressed our force at our AY, we now need to express our force of our distributed load. Since we know it's a constant, using our order of lines, we know we're now going to express it as a linear problem. To do this, we can figure out what point it's going to reach by simply taking the area under the curve, which is our simple calculation from earlier of the force over the distance it's applied as. And we'll get that this force equals 3. Since we start at 0.75, we're going to subtract 3 from that 0.75. And we're going to find that we're going to reach 2.25 negative. And last, we need to account for our force at our CY. We know that this should equal what our new point is at, and it should return us back to 0. And since our 2.25 of our force is the same as our 2.25 that we're at now, we know that we've done it correctly. Now we are ready to express our bending moment diagram. Since we know bending moment is just the integral of our shear force, we can simply calculate the area underneath our lines. We can see that we have 3 different regions. Our first rectangular region, our second triangle region above the x-axis, and our third triangle region below the x-axis. First, we're going to calculate the area underneath the rectangular portion. To do this, we can simply multiply by our force over the distance that it's traveling, which we know is 2 meters from our diagram right there. And we'll find that this will reach at 1.5. Since this term is a constant, using our order of lines, we need to express this as a linear term. Now that we found the first region of our shear curve, we're going to move on to our second region, which is this first triangle. Using the same method, we're just trying to find the area above the curve using the area for a triangle, which is 1/2 base times height. We already have our height, which is expressed by our force of 0.75. We just need to do a simple calculation to find our base. To do this, we're going to take our 1.5 from our distributed load and divide by the force we're currently at of 0.75. We should get 1/2. Now we can plug this into the equation of 1/2 base times height, to which we should get 0.1875. Since we're still above our x-axis, we know that this is acting in the positive direction. So we're going to add this to our 1.5 from earlier, to which we should get 1.6875. Since this is a linear region, using our order of lines, we know we now have to express this as a quadratic. It's important to pay attention to the concavity of our quadratic so that we can plot it correctly. We know that since this is the larger region, it's going to have a larger initial thing and it's going to concave down. Lastly, we need to find our third region expressed by the triangle underneath the x-axis. Using our same method, we know that our distance is the remainder of our 2 meters, which should be 1.5, times our force, which is 2.25, times 1/2, to which we should get 1.6875. It's important again to remember to graph our linear region as a quadratic with respect to the concavity. Since our larger portion is towards the end, we know that we're going to have a more drastic slope towards the end of our graph. We also know that we did our calculations correctly because our numbers of 1.6875 and 1.6875 got us back to 0. It's important for engineers to be able to analyze both of these graphs to correctly pick materials when doing a project. If not, their material could fail, causing their project to fail.